Welcome to AI Paper Slot. Today we are getting right into a fascinating paper. It is called RoboTTT, which stands for Context Scaling for Robot Policies, and it's linked to researchers at NVIDIA.
Yeah, and this one is, it's really a massive breakthrough for the field.
It really is. So for you listening, if you've been following the machine learning world, you know everyone is obsessed with scaling the context windows of large language models, right? Getting them to read whole books at once.
Right, exactly, like millions of tokens.
Yeah, millions of tokens. Well, this paper takes that exact same concept and applies it to physical robots. And by scaling up that context window, they've achieved continuous autonomous task execution for up to 5 minutes.
Which, I mean, if you work in robotics, a 5-minute execution window without human intervention is an absolute eternity.
Oh, totally. Because traditionally, robots suffer from this severe case of artificial amnesia.
Yeah, a 10-second memory limit.
Right. Imagine a robot is making you breakfast. It cracks the eggs, gets the toast going, and then 10 seconds later, it just stops. It stands there completely forgetting why the pan is hot or that it is even making breakfast at all.
It just loses the overarching goal entirely. And that's exactly what RoboTT fixes.
Let's talk about what this actually looks like in the physical world. Now that we know what the breakthrough is, what is the setup?
So in the visual data they provided, you see this highly complex bimanual manipulation environment.
Bimanual meaning 2 arms.
Yeah, exactly. 2 sleek, white robotic arms with black joints and these standard 2-finger grippers. And they are working together in a shared workspace.
And they have cameras on them, don't they?
They do. Wrist-mounted cameras right above the grippers. So the whole system is basically relying on this egocentric visual stream.
Meaning it's seeing everything from the perspective of its own hands.
Right. Taking in the visual data exactly as its hands are moving.
Okay, so what are these arms actually doing? Yeah.
Well, one of the primary long horizon tasks they showcase is building these electronic snap circuits. It's on this clear plastic base with a hexagonal grid.
Like assembling little electronic toys, basically.
Exactly, but it requires really high precision. So first, one arm fetches an Amazon Basics battery pack, orienting it perfectly to snap it into the grid.
Okay.
Then it reaches over, retrieves a motor, connects that to the battery, and then finally, and this is the really delicate part, it places this tiny red propeller directly onto the motor shaft.
Wow. And I think the key for you listening to understand here is this strict sequential dependency of all that.
Oh, totally.
I mean, you can't place the propeller until the motor is secure, right?
Exactly. And you can't power the motor until the battery is seated.
Right. And under that old 10-second memory paradigm we were talking about, the moment the robot snaps the battery into place and turns to grab the motor,
it completely forgets about the battery.
Right. The visual information of the battery's location just starts falling out of its working memory. It becomes functionally blind to what it just did.
It's basically like, well, for the ML engineers listening, think about earlier generations of robot policies as coding with a 1-line memory limit in your terminal.
Oh, that's a great analogy.
Yeah. You type a command to place the battery, you execute it, and then your terminal history is just wiped clean immediately.
So by the time you're on step 4, you're holding a red propeller with literally zero context for what you're actually building.
Right, exactly. But RoboTT acts like a developer with the full IDE open.
It remembers the whole project.
Yes. It remembers that placing the battery 5 minutes ago was just step 1 of this much larger blueprint to eventually spin that propeller.
So the variables actually stay in active memory. But wait, how do they actually teach the robot this sequence? Because writing a hard-coded state machine for a 5-minute circuit assembly would take, months, right?
Months of engineering, yeah. And it would be incredibly brittle.
Like if a plastic block shifts 2 millimeters, the whole script fails.
Exactly. So they don't do that. The visual evidence shows human hands physically performing these exact tasks in the workspace.
Oh, so they are physically doing it first.
Yeah, placing the battery, spinning the propeller to test it. They are leaning heavily on imitation learning.
Okay, so feeding the network massive sequences of human teleoperation.
Right, capturing that continuous kinematic data. But historically, imitation learning had a major limitation here.
Which is what? Because of the memory bottleneck.
Yeah, the quadratic memory scaling of transformers. If you fed a smooth 5-minute human demonstration to an older model, the architecture just couldn't digest the overarching logic.
It would just blow up the VRAM.
Exactly. So engineers had to artificially chop the human's continuous motion into these isolated tiny chunks.
Like turning a smooth movie into a choppy flipbook.
A flipbook where half the pages are missing, yeah. So the model learns how to insert a battery, but it never learns why that insertion leads to grabbing a motor 2 minutes later.
It misses the overarching goal.
Right. But RoboTTT introduces an architecture that lets the model swallow that entire 5-minute sequence as one continuous chain of causality.
Okay, that makes sense. So snapping blocks onto a static grid is an incredible proof of concept.
Oh, for sure.
But the environment is predictable, right? Like once a block is snapped in, it's stable.
Yeah.
It doesn't fight back.
No, it doesn't.
But the paper transitions into this second experiment that is just, I mean, it demands a totally different level of spatial awareness.
Oh, you mean the toy car?
Yes, the toy car and the active tool use,
Yeah.
which is basically the holy grail for general-purpose robotics.
It really is. The setup is way more advanced. You have these robots working on a blue toy car chassis with yellow and red accents.
Okay.
And then the researchers introduce a red and yellow toy power drill.
A functional power drill.
Yeah, a toy one, but
Yeah.
functional. And it requires fully bimanual coordination.
Meaning both arms have to work together perfectly.
Exactly. One robotic arm descends and physically clamps down on the blue chassis to hold it secure, while the other arm grasps the power drill, positions it over a wheel, and actively applies it to the car.
Which, when you think about it, introduces a nightmare scenario for physical AI.
Because of the noise. High-frequency noise.
Right. When you pull the trigger on a power drill, the whole tool vibrates violently.
And the robot's arm vibrates too.
Exactly. And most critically, that wrist-mounted camera we talked about earlier, it starts shaking.
So the egocentric video feed gets completely blurred.
Yeah. And if a traditional model's context window drops at that exact moment,
It's game over.
it wakes up with amnesia,
Yeah.
feels a massive vibration, sees a blurry image, and basically panics.
Because it forgets why it's holding a vibrating piece of plastic.
Right. It forgets that it pulled the trigger in the first place.
And it forgets what the other arm is doing.
Oh, right. The arm holding the car.
Yeah, if that dynamic cross-attention between the two arms fails, the left arm might just stop applying counterforce.
And then the drill just catches the plastic and violently spins the toy car right off the table.
Exactly. The left arm has to constantly, dynamically adjust its grip to resist the changing torque from the drill.
So this is where we need to ask, how are they actually doing this computationally?
Right.
Because we established that processing real-time, 30 frames per second video and torque data usually blows up the VRAM.
It does, yeah.
And a vibrating drill isn't just background noise, right? The vibration is the actual feedback telling the robot the tool is working.
Right, it needs that data.
So do they just brute force this?
Yeah.
Are the NVIDIA-linked researchers just throwing a 100 billion parameter model at it and burning down a server farm to compute everything?
They absolutely do not, because real-time robotics just cannot afford that kind of latency.
Right, if you have a half-second delay.
The drill has already stripped the screw or broken the car.
Wow, yeah.
So the architectural secret sauce here comes down to two critical citations in their methodology, MiniCPM and ruler.
Okay, let's break those down for the technical listeners.
Yeah.
'Cause MiniCPM is fascinating.
It really is.
It proved that you don't need a trillion parameters to get high reasoning in language models, right?
Yeah, as long as you use incredibly efficient data packing and latent compression techniques.
So how do they apply a text model compression strategy to video and torque data?
Through spatial and temporal pooling.
Okay. What does that mean in practice?
Basically, they aren't treating every single pixel of that shaking video stream or every micro fluctuation in the torque as an equally important token.
So it's not trying to hold all of that in active memory for 5 minutes.
Exactly. The architecture maps all that continuous visual and kinematic data into a highly compressed latent space.
Oh, I see.
It learns to filter out the high-frequency execution noise like the drill vibrating or slight lighting changes, and it only retains the high-level semantic tokens in its long context window.
So it compresses the raw data. Like instead of pixels 40 through 80 are blurring rapidly, it creates a stable internal representation of I am successfully operating the drill.
Yes. It isolates the overarching task signal from the noisy physics of actually doing it.
That is so smart. It builds a hierarchical understanding of time.
Exactly. It uses short-term, uncompressed, high-frequency attention just to keep the drill bit securely in the screw head in the present moment.
Right.
But it uses its scaled, highly compressed 5-minute context window to remember the overall plan.
Like remembering that once this screw is done, it has to move to the back left tire.
Precisely.
But wait, if you pool the data that aggressively to save memory, don't you risk compressing away important details?
That is huge risk, yeah.
So how do they prove the model is actually remembering the specifics of the workspace and not just like hallucinating a sequence of events?
That is where the second citation comes in, the ruler benchmark.
Ah, okay.
Yeah.
Because in the LLM space, Ruler is explicitly designed to test the real context size of a model.
Right. It stops companies from just claiming they have a 1 million token window if the model can't actually retrieve a specific fact hidden inside it.
The classic needle in a haystack test. But how do you translate that to physical robotics? I mean, a robot isn't looking for a hidden word in a textbook.
No, but for RoboTTT, the needle is a highly specific physical state from the past.
Oh, okay.
By holding themselves to the ruler benchmark, they prove the model can retrieve spatial and temporal needles from its physical haystack of context.
Give me an example of what that looks like.
So imagine the robot placed a tiny screw on the edge of the table at minute 1.
Okay.
And then it spends 3 minutes dealing with the vibrating drill and moving the car around.
Lots of noise.
Lots of noise. But at minute 4, it needs that specific screw.
Right. So the ruler benchmark proves the model can actually reach back into its compressed history.
Recall the exact spatial coordinates of that screw from 4 minutes ago.
And just go navigate back to pick it up. Completely unbothered by all the crazy data that happened in between.
Precisely. It proves the robot has a genuine working episodic memory.
That is wild.
It doesn't need to hold every microvibration from minute 2 in its active context. It just needs to reliably fetch the step-by-step state history.
So they essentially combine the highly efficient, scalable training of small models, like MiniCPM.
With the rigorous long context retrieval of Ruler.
And the result is a policy fast enough for real-time motor control, but deep enough to execute a 5-minute plan.
Exactly.
Synthesizing this for the ML practitioners listening,
Yeah.
the hardware we saw in the visual data, those sleek white and black arms, it's fantastic engineering.
It is, yeah.
But it's not fundamentally new physics.
Mm-hmm.
Like, we've had the physical actuators capable of building a circuit board or operating a power drill for years.
Oh, for sure. The physical actuators were never really the bottleneck.
Right.
The bottleneck was always the brain. We just didn't have a policy that could hold the blueprint in its head long enough to finish the job.
Without losing its place.
Yeah,
Which means the frontier in robotics is clearly shifting.
it really is.
It's no longer just about building better mechanical hands or stronger servos. It's about giving the agent the contextual memory to actually sustain an action plan over time.
Because curing robot amnesia is what ultimately unlocks complex multi-step assemblies
And active tool use.
and genuine autonomy in unpredictable environments.
Yeah. And looking forward, applying LLM context scaling techniques to robotics raises a truly wild question about where physical AI goes next.
It does, because, we are celebrating a 5-minute context window today because it's a massive practical leap from 10 seconds.
Right, it's huge for robotics.
But in the language model world, context scaling didn't stop at a few pages.
No, we now have models with 1 million token windows. Yeah. Capable of processing entire libraries of text all at once.
Exactly. So if this token scaling architecture continues to map successfully to visual and proprioceptive data,
What happens when we hit the equivalent of a 1 million token window for physical robots?
that's the crazy part. Because if a robot is operating over days or even weeks in a dynamic environment like a warehouse or a home,
Even a massive context window will eventually max out, right?
it has to, yeah. But think about biology. When insects like ants need to operate over long time horizons, they use this mechanism called stigmergy.
Stigmergy. Okay, what is that?
It's basically when they leave physical pheromone trails to offload their memory into the environment itself.
Oh, wow.
They use the world as their memory bank.
So will future robots start physically altering their environments to compensate for their context limits?
It's entirely possible.
Like arranging their tools in specific semantic patterns? Or literally leaving physical bookmarks in the workspace?
Just to offload their massive memory banks into the real world.
That is fascinating. The environment itself becomes an extension of the model's memory.
Specifically.
Meaning,
Yeah.
we might have to start designing our factories and homes not just for human convenience.
But as external hard drives for robot context windows.
Wow. Well, that is definitely something to keep you all up at night as you go back to training your models and tweaking your architectures.
Absolutely.
Thanks for joining our deep dive into the research today. We will catch you next time on AI Paper Slop.